What we're here to talk about today is the tooling for Darryl Nelson's Bear Head that Mark so aptly showed us. Here we have 12 tools, and your tooling or your bear head, hang on, let me get my laser pointer because I just realized I'm pointing and no one can see. Your bear head is going to have your artistic impression. So the tooling is going to reflect that. I have heard from more than one source that when Darryl Nelson teaches this class, he gives his student half a day to make the tool. So keep that perspective in mind. The handout that was attached to the invite is my attempt to give you tracing or an outline of the tools, and keep that in mind. You might want them a little different size, or some of them might be a tracing, so the actual outline is a little bigger and the tool would fit inside. But I gave you that because I know no matter how much I tell you that, these tools are yours to shape as you will, you would have wanted those particulars. So I provided those. And if you have any questions about the handout or anything, just let us know and we'll try to answer those questions. Another way to think about all this tooling is it represents your thumb, and you're just pushing material around like you do with clay. And if you don't like the push it provides, switch it up a bit. Either make a new tool, modify your tool, whatever, and then try them all out in plasticine so you can get a cool looking bear like Carol just showed us. Our tool length that we want to shoot for is about 8.5 inches long. You're working with hot stuff. You are going to work with a glove on, but those gloves can heat up too. So the 8.5 is about the right length away from the hot metal and still being able to use it easily. It's not a must do, but in general, that would be what I would recommend shooting for. And some tools you're gonna taper them out about 1 inch. Some tools you're gonna taper them out a little more than that. So some of those you're going to want to taper out a little more than that. And so you would cut that 2 inches shorter than that 8.5 inch, so 6.5 inches. One tool, and we're going to bring this up a couple times, John and I, we're going to recommend that it's a little different material. But if you want to just use 4140 for that particular tool, and it's the medium curved chisel, you'll just need to cool it more often. That's all. So let's dig in. We are going to be using a little higher carbon steel with some other additives to create tools that will last, right? That's the whole point. We want to be able to use our tool over and over. These additives make the metal harder to work than mild steel. And if you think about that from the perspective of the factors that affect the penetration of your hammer blow, how hot your material is, how hard you hit, what metal, and the location, or we know right off the bat that your hammer isn't going to penetrate this tool like it does mild steel. There are other hard steels out there, but we are recommending this 4140 or sucker rod, which can be 4140 or 4130 and some other things, but all of them would be reasonable for this set of tooling. The reason why we're recommending that is you can find it used, therefore you can find it a little cheaper. You can get it from a drilling company's scrap pile. It's 0.4% carbon. That's the 40 in the 4140. That's the 0.4% carbon. The 41 tells us that the additive to the iron is chromium and molybdenum, which most people shorten to chromoly because who wants to say molybdenum a lot? So what this does, that chromoly does, it allows us to quench the tool while working and we don't lose our heat treatment. as long as while you're working it, you keep it cool. Like, don't let it turn a color. Don't let it get to a temperature that would cause it to lose its heat treatment. Now, this hardness and these other additives come at a price, and that price is that it must be forged at the right temperature. If you get it too hot, if you see sparks, you're losing carbon. You can even get it so hot it's going to kind of crumble. So you're just eating into any hardness potential, and the tool's not going to turn out as it's not going to turn out to be a tool you can use. The other is you can't work it too cold or it will crack. And then finally, you need to make sure that you run this tool, this steel, through the paces necessary to get it into the most durable state possible. And those steps are called heat treating. And I'm going to walk you through all of that because it's really one of the more important parts about making these tools. But let's not throw around opinions. I'm not a metallurgist. You're probably not a metallurgist, or at least I hope there aren't any in the audience. And I don't want to deal in opinions. So there is a chart that was made so that we can all be on the same page and understand what each other are talking about. And that chart looks like this. It's our basic guide to ferrous iron metallurgy, and it deals in the different percentage of carbon down here at the bottom. And I stuck it up on the website under resources and technical documents. So what the chart says and what you already know, in fact, I would venture that you know most of what is on this chart already, is that metal behaves in a predictable manner. In fact, I like to think of it as a tattletale because the result you get is kind of telling on you. It's the metal telling on you, and it's telling you or anyone else who might be observing what you did. This guide helps us understand those behaviors and what to expect from our. So I'm going to say it again, and you're going to hear it a lot. Steel has different states depending on how hot it is, sort of like water that turns to ice or boils at different temperature. It's the same with iron and steel. I mean, that's why we're heating it, right? We're heating it because we want to take it through this transformation range. It's not magic, but above that, that's when suddenly it's bendable with very little effort on the smith's part. And the only issue with this concept that I have found is that unlike, when water gets really cold, it's ice, and when water is really hot, it's boiling, and you can just tell. The only thing we have to go on is the color, and then either our own experimentation or some people look at all this under a microscope to tell what's happening to the metal. So unless you're melting it, unless you're up here in the burning range and you've got it to this white heat range, and then it's changing property is visible to the naked eye. So unless you're doing that, well, you can't tell. And if you are up here, hopefully the naked eye has eye protection. All right, well, let's look at this chart and let me remove some of the things I'm not going to talk about. You're already aware of some of these things, and I've mentioned them. You've got your burning range, you've got your forging range, but what I want to turn your attention to in terms of what you need to know when you're forging any metal, or in specific, the 4140, is this range down here, and it's your black heat range. It is called the blue brittle range, and it has a little number 9. And the number 9 corresponds to some words out here. So let's blow that up and take a look at it. The blue brittle range already sounds a little ominous, right? Like danger, danger. So what it says, what number 9 says, is that the blue brittle range is this 300 to 700. And working of steels should not be done between these temperatures since they are more brittle in this range. Brittle means it's going to cause cracking. So do not hit it in this range. That's true for all iron, and the chromoly exacerbates this problem. So if you have ever worked a knife with a little higher steel, a little higher carbon in your steel, and the tip fell off, like just randomly, you didn't even realize it was about to fall off, that you just got tattled on. You were working it in this blue brittle range. So no forging, don't change the size, the cross section of the metal when it's in the black heat. So again, all these tools can be made from this 4140, but there is one tool that we're going to ask a lot of. And what we're asking it to do is we're asking it to be super thin. And then we're asking it to be in the bear head's mouth for a long period of time. So it's going to get really hot. So between the heat and the thinness, that's going to cause some problems. If you're using 4140, you would want to quench that often. Usually when you're using a tool made out of the sucker rod or 4140, you'd quench every 3 hits. If you're doing this maneuver with 4140, every 2, or the amount of time it would take you to do 2 heats. Because remember, you're going to be putting it in there and kind of lining it up. So quickly cool it with 4140. However, H13, which we're recommending, or we're going to discuss here tonight, has more chromoly and another additive that makes it so that it can withstand those heat cycles, like the heating and cooling. It can be water quenched, as long as you don't let it get a color. Like, don't 4140 or this, don't let it get a color and then quench it. You've totally changed the property of your steel. But it's designed to be thermally shocked. So that is why we're saying H13 for this particular tool. And the big caveat with this is that it needs a special heat treatment. And John is going to talk about that. I'm going to talk about the heat treatment for the 4140. But the bottom line is the struck end is the issue. Improper heat treatment can cause this tool to be too hard, which will lead to the tip exploding. You never want to hit hard with hard. This steel gets so hard that it's almost like hitting a hammer on a hammer. And that's a big no-no. So it's best not to get that struck end heated in the first place. All the forging, if you notice on this tool, all the forging is done on the working bit. And this mushrooming on the end is telling us that this tool, this struck end, was soft enough because it moved when we hit it. It didn't explode. So let me get into some heat treatment, and I'm going to spend a couple minutes on this, several minutes on this, to make sure that you understand this very important factor of making hand tools. I mean, that hand tool needs to last a while, and besides, it's what blacksmiths do, right? So a good understanding of heat treating and a little bit about the why is going to help you go a long way with this. There are 3 steps to heat treatment. And I think a lot of people think there's just one step, but the 3 steps are normalize, which the word kind of describes it, like you're making it normal. You're getting it back to its relaxed state. And then there's harden, make that tool as hard as it can be. And then there's temper. You're going to back off that hardness a little bit. And this harden and temper is not one step, even though you can do it in one heat. So I'm going to go through these 3 steps using some of the language of the metallurgist, which means you're going to be hearing some terms you don't find included in everyday conversation. So back to our little chart. The heat treatment and the normalizing can be found on this chart. First, we need to know the amount of carbon. It's got the percent carbon. Ours is 0.4. That's the 40 in the 4140. And I drew a nice little line up for us. And what does the chart say about normalizing? And it's right here, annealing and normalizing. And I'll blow this up in a second. The annealing normalizing, which corresponds to number 4 and number 5, says that consists of heating tools to slightly above AC3, holding for austenite, then slowly cooling to get our small grain size. And they even drew them here for us. Here's our small grain size. Notice they get bigger as we get hotter. Our small grain size, softness, good ductility, and other desirable properties. On cooling slowly, we get austenite back to its softest possible form, and that's this ferrite and pearlite. Annealing is a little fussier. It takes a really long time, sometimes even a day. So I'm going to steer us towards normalizing. And the normalizing, it's the same steps. You heat it up to austenite, heat it up to this line here, and then cool it slowly. So don't get thrown off. Hold on, I'm going to mute myself because I had to cough really bad. Don't get thrown off by the language of the metallurgist. And in this application, we're talking about this word austenite. Might not be a word you've used or heard before, but you have used the word Austin before, and it is Mr. Austin, somebody that noticed this particular trait. And it's also really not new information. You're already aware of what happens when you heat up metal. It transforms, and all this hidden under my circle is the transformation range, this little spot right here. And it's a range because the metal isn't all one element. I already told you that there's carbon, chromium, molybdenum in there, in addition to the iron. So there has to be a range during which this whole business can change to the property that makes it malleable, the property that we can forge. I like to think of it as how when you're cooking, boiling water lets us cook, but your potatoes are going to take a lot longer than your spinach. So the whole thing has to cook a while before it's done transforming. So that property or state we're looking for is right above that range, and that property has a name called austenite. So let me make this larger. I drew in our line for our 0.4% carbon. We have our lower transformation temperature here, which is just below the 1400, and along our percent carbon range, we get to our upper transformation temperature, which is on a slant at just above 1500. Right above that, when it's all austenite, and that's what our normalizing is. We want to get it above this AC3, and that C, don't let the C throw you off. They mean this A3 line. The C just means catch it on the way up, and it's the first letter of a fancy French word. Well, it's probably a normal word for the French for heating, chauffage, which Beatrice will probably tell me I'm not saying right. But once we get it above here, above that AC3, and we hold for austenite to form, then we need to let it cool slowly. And here, when we're talking about the transformation range in heat treatment, here's where I find most people say, can't I just use a magnet? Like, doesn't the magnet do it all for me? And I've got two things here to point out because it's on the chart, but one of them that isn't on the chart is using the magnet is kind of fussy. Once you check for the magnet, now you've lost the heat, and it doesn't allow for the soak time that you need to make this whole thing work. The other thing, and to me, this is the bigger factor, is that the magnetic point is right here at the 1420 range, which is right here, which you've probably already noticed is below our upper transformation line and below our annealing and normalizing line, which that's about 150 degrees. So no, the magnet doesn't tell us when we got here. What it does do, and I would recommend you use the magnet for, is to start to learn what color your metal is in your forge, or maybe even a new forge, when your metal goes into that transformation range. That's what the magnet tells you. It tells you how to read that color. So in the simplest of terms, normalizing is relieving the stress created by what you've just done to it: heating, cooling, whacking, heating, cooling, whacking, heating, cooling, whacking, which causes those normally neat little structures to get all warped out of shape. This also happens when you're grinding or machining. If you do a lot of that, you may need to get your metal material back to its normalized or stress-free state. Think about what would happen if we all went for a long run, which I wouldn't go. So if you all went for a long run, you're going to feel, and I'm talking like a marathon, you would feel a lot better after a hot tub than just plopping down the couch and having a burger and fries. So it's kind of like that. We sent our metal off on a marathon, and now we got to let it soak in a hot tub. So these are the steps: transformation range, soak there for a bit, and then allow it to cool slowly. And by cooling slowly, I don't mean chuck it on the floor. That is actually a quench. It's an air quench. I mean cool slowly with some heat still applied. And that is set it near the fire in your forge. For propane, you can put it on top of your forge. So now the test that you've achieved this softer state, and the activity you can do is you can file it. You can now file your tip, and the file should bite into that metal and allow you to file it fairly simply. So let's move on to harden and temper.